Okay, this is chapter 23 notes. Series circuits, first of all, we'll talk about series and parallel. For series, the main thing you need to know is that for resistance, you add them up. So keep in mind that series is when you're hooking resistors or elements of the circuit, which we can a lot of times just look at as resistors, like a light bulb, for example. When we hook those up, we hook them up like this, where all the current has to go through each one. We'll look at some examples and we'll determine what happens basically with the voltage drop across each circuit. All the current is going to be the same through all of them we'll establish. And then the resistance, the equivalent resistance for the circuit is going to be these added up. So, if each of them are 10, for example, then the equivalent resistance for the circuit would be 30 ohms. So we'll say R sub EQ for equivalent resistance. All right, so then when we want to find the current, for example, we can take the voltage of the power source and divide by the equivalent resistance for the circuit, and that will tell us how much current is going through, because the current is not going to vary at all in a series circuit. So here's an example then. Let's say we've got two resistors here. We've got one that's 47 ohms, and we've got one that's 82 ohms. If we want to find the current in the circuit, what we can do is take the voltage of the battery, which in this case is a 45 volt battery, and we can divide by the equivalent resistance for the circuit, which in this case the equivalent resistance is the two added together, 129 ohms, and that gives us a current of about 0.35 amps. And then we can find the voltage drop across each resistor. And how we do that is we just use Ohm's law on each resistor. So we'll use V equals IR. And the current is 0.35 amps going through both, and the resistance of the first one is 47, so that gives us about 16.4 volts. And then when we do the same thing with the other resistor, just take the current that's in the circuit, about 0.35 amps, and multiply it by 82 now, and you get the voltage drop across the other resistor, which is 28.6 about. And you'll notice these add together to be the voltage of the battery, so you can kind of look at it as charges come out of here with a certain amount of energy per charge of 45 volts, and they drop 16.4 joules per coulomb of energy through the first resistor, and they drop another 28.6 joules per coulomb of energy through the second resistor. And then they kind of gain that energy back again as they go through the battery. The book uses an analogy of a waterfall, which is kind of, it's like, this is where you bring the charges up some height and they fall back through this resistance and this resistance, or they lose energy through those spots. So part C then says, if the 47 ohm resistor is replaced by a 39, will the current increase, decrease, or remain the same? In that case, the current will increase, because in this first formula right here, now we're decreasing the equivalent resistance for the circuit by lowering the resistance of one of the resistors. And if we decrease this number in the denominator of this fraction, we obviously increase the current, which makes sense. In series, it's pretty easy to understand. If you decrease the resistance, you're going to allow charges to flow easier, and so you'll increase the current. So we'd say increase for here. And then part D, what's the new voltage drop across the 82 ohm resistor if we replace this with a 39? So we would go back through and redo this calculation, only now instead of using 129, we'd use 121, which would change our current in the circuit to now about 0.37 amps. And I would now multiply that 0.37 times the resistance here of this resistor to find the voltage drop. And this number would now change to 30.5 volts. So basically we can use two resistors in series to be a voltage divider then. So this question says, what's the voltage across the 470 ohm resistor for the next example here? So once again, let's use the current is going to be equal to the voltage divided by the equivalent resistance, just V equals IR. So this is like V equals IR for the total of the circuit, in which case the voltage in the circuit is 9 volts. The equivalent resistance for the circuit is the 2 ends of 860 ohms, and that gives us about 0.01 amps. And so if I want to find the voltage across just the 470 resistor, I would now do V equals IR again with just this resistor. So the current is going to be 0.01 about through here, multiplied by the resistance of 470, and that gives us about 4.92 volts. So if we took our voltage probe in the lab and hooked it up here over this resistor with this exact same setup, we'd read about 4.92 volts, or our multimeter and hooked it up here. If we hooked it up across the whole thing, obviously we'd experience 9 volts. Our reading would be 9 volts. But just across one resistor, we're going to get just 4.92. Okay, so now if we hook up a parallel circuit now, what's different is the voltage across the battery is exactly the same as the voltage across each resistor. Because you can kind of tell it doesn't matter whether you hook the voltage probe up here or whether you hook it up here. You know, there's no resistor in between necessarily to change anything. So it's going to give you the same voltage reading of 120. And that's the advantage of hooking things up in parallel, is you're not basically losing energy per charge from the other items that are hooked into the circuit. So you're supplying 120 joules per coulomb of energy to each of the items in the circuit, to each of the resistors or each of the appliances or whatever it is you're hooking in. So then from there you can see what happens is current splits up then. So some of the current's going to go here, some of the current's going to go here, and some of it's going to go through here. And you'll notice that current wants to follow the path of least resistance. So most of the current goes through the smallest resistor, the 6 ohm resistor. And then not quite as much current goes through the bigger 9 ohm resistor, and the biggest resistor has the least amount of current. So let's do an example where we find, for part A, the current through each branch of a resistor. Let's say we have 3 devices plugged in, one with 60 ohm resistance, one with 30 ohm, one with 20 ohm resistance, and we have a 90 volt battery. If we want to find the current through each of these branches, what we can do is use V equals IR for each one. So the voltage is going to be 90 for each of these, and the resistance of the first one is 60. So divide both sides by 60 and you get 1.5 amps. And obviously we can do the same thing. That's for A. So for B, we're going to do this exact same thing. We're going to take 90 and this time divide by the 30, in which case we get a current going through B of 3 amps. And then for C, we're going to take 90 divided by 20, so we get about 4.5 amps. Now part B wants us to find the equivalent resistance of the circuit. So to find the equivalent resistance in parallel, we've talked about this. What we do is we take use this formula, which is on the formula sheet: 1 over resistor A plus 1 over resistor B plus 1 over resistor C. So each of these items then I'm going to plug in the equivalent resistance. For A, it's 60, for B it's 30, and for C it's 20. So you have to solve this equation. I would just add these together in your calculator and then take the reciprocal of it. So you do that in your calculator. You get 1 over the equivalent resistance equals 0.1. Flip both sides and you get the equivalent resistance is 10 ohms for the circuit, which makes sense because if you add these together, 4.5 plus 1.5 plus 3, you get 10. So it makes sense that you got 10 amps of current running through here, and then part of it splits out here, and 1.5 amps go through here. Part of it goes through B here, which is 3 amps, and part of it goes through C, and the most current, 4.5 amps, goes through that branch. So the current through the battery is actually 10 amps. Okay, so we'll talk a lot about applications of circuits as we actually do the homework problems, because with each individual problem, we'll be able to talk about, okay, what happens when we plug in a hair blow dryer, for example, with a certain amount of power or a certain amount of resistance. But some terms we're going to want to know, some vocab, is short circuit. This occurs when a circuit is very low resistance is formed. And a circuit with low resistance, obviously, we're going to have a lot of current, and so much so that we're going to break a fuse or a circuit breaker in many cases. A fuse is just a short piece of metal that melts when too much current goes through it, like what you'll find in your car. A circuit breaker is an automatic switch that detects changes in current and then breaks the circuit, which I'll show you in a second. And a ground fault interrupter is, you see these in your kitchens and your bathrooms because building codes require them to be in kitchens and bathrooms. But you might find them elsewhere in your house as well, anywhere you're going to plug in expensive devices as well, because what they do is they detect changes in current and they shut the circuit off at the actual outlet. So it's like an added line of defense if you have a surge of power, say your grid gets struck by lightning or something like that. It's an added safety feature. So a circuit breaker is unlike a fuse where metal doesn't actually melt, but what happens is the metal can set off a mechanical process here that opens this circuit. Okay, so here's one more example then before we start the homework. Let's say we have a 120 volt source. We're going through a 1.5 ohm resistor in series, and then we have two parallel. We have a hairdryer and a lamp hooked up in parallel. The question is find the current through the lamp. So we're looking for the current right here. So what we're going to do is we're going to reduce this circuit. First of all, I'll replace the voltage supply with the battery symbol. What I'm going to do is redraw this so that I have two resistors in series. So what I'm going to do is add these together in parallel to get basically one resistor. So the way I do that is with the formula for equivalent resistance in parallel. 1 over resistor 1 plus 1 over resistor 2. And these resistors are 12 and 125. Okay, I'm going to add these together and then take the reciprocal to find the equivalent resistance, which is in this about 10.95. So basically we can look at these two added together equal about 10.95, and this is still 1.5. So I can find the total resistance for the circuit by adding these together, and that gives me about 12.45. So the total resistance for the circuit, I'll say equivalent resistance for the circuit is 12.45 ohms approximately. I can now use V equals IR with the entire circuit, so the total voltage and the total resistance over equivalent resistance, which is 125 equals current times the total resistance for the circuit, 12.45. That gives me a current of about 10.04 amps. So that's the current that's going through right here. And obviously all the current has to go through here. And now the current splits up. So let's look at how much potential difference we have across here and here and here and here. And the way we can do that is by finding the voltage drop across this first resistor. So if the current going through here is about 10.04, we can use V equals IR in this part right here. So the voltage is what we're looking for. We have the current of 10.04, and we can multiply that by a resistance of 1.5. And that gives us a potential difference drop of about 15 volts. And so what that means now is we have about 110 left. There's about 110 volts now across this part and this part in parallel. So we can use that number. So we'll take the total 125 minus this number we got in the calculator, which if I don't round this, keep that in the calculator, it's about 110 or about 109.9 volts. And now I know the resistance for that too. The resistance for that same spot is 12, but they want this one. So we want the current through this part. So instead of using the 12, I'll use the 125. So now I know the voltage and the resistance in this branch right here. So I can find the current by using V equals IR for that branch now. So the voltage is about 109.9. I'll keep that in my calculator. And the resistance is 125, which if I divide, that gives me a current of about 0.88 amps through this part right here. All right, let's try some homework problems and see if that helps.